In 1993, three engineers sat in a booth at a Denny's diner in San Jose, drinking bottomless coffee, sketching out a company almost nobody believed the world needed. Their idea was simple and strange. Build a chip that did only one thing: draw triangles on a screen, millions of them, faster than any human eye could follow. 3 decades later, that same company would sit at the center of the most valuable technological race in human history. To understand how, you have to understand a difference between two ways of thinking. A traditional computer processor, the CPU, is like a single brilliant mathematician at a desk. Give it a hard problem and it solves it, step by careful step. A graphics processor is something else entirely. 10,000 schoolchildren in a stadium, each handed one small sum, all answering at the same instant. No single child is clever. Together, they are overwhelming. Because that is what an image is. A grid of pixels, each one asking the same question: what color am I? And each answer independent of the rest. Through the 1990s, NVIDIA built these chips for teenagers. Video games, dragons, spaceships, muzzle flashes rendered in a dark bedroom at 2 in the morning. It was a brutal business, dozens of rivals, thin margins. NVIDIA nearly died more than once, weeks from running out of cash. Then, in the early 2000s, something unexpected happened in university laboratories. Physicists and chemists began noticing that the maths of a video game, vast grids of numbers, multiplied over and over, looked exactly like the maths of their own research. Weather models, protein folding, oil reservoirs, star formation. All of it, at heart, matrix multiplication. So they began smuggling their equations into graphics cards, disguising scientific data as colored pixels, tricking the hardware into doing physics. It was clumsy, it was absurd, and it worked. In 2006, NVIDIA made a decision that would define the next 20 years. It gave those scientists a proper door. That door was called CUDA. A software layer that let any programmer write ordinary code and have it run across thousands of tiny processors at once. No pixels, no tricks, just raw parallel computing handed to anyone with a laptop and a graphics card. Wall Street hated it. CUDA cost billions and served a market that barely existed. For years, analysts asked why a gaming company was funding academic software. The answer arrived in 2012 in Toronto. A student named Alex Krzyzewski trained a neural network to recognize photographs, cats, mushrooms, sailboats, using 2 consumer gaming cards bought off a shelf. His system did not just win the competition, it humiliated it, cutting the error rate almost in half overnight. Because a neural network, stripped of its mystique, is nothing but numbers arranged in grids, multiplied and added billions of times a second. The same operation that shades a dragon's wing also teaches a machine to read, to speak, to recognize a human face. By accident of geometry, NVIDIA had spent 20 years building the perfect engine for artificial intelligence, before anyone knew it was needed. Consider what happens inside one of these chips today. A modern data center GPU holds more than 80 billion transistors, etched in patterns thinner than a virus on a slab of silicon the size of a postage stamp. Stacked beside it sit towers of memory, feeding numbers in and out at terabytes per second. The true bottleneck, the narrow neck of the hourglass. And because one chip is never enough, thousands are wired together with high-speed links until an entire warehouse behaves like a single, enormous brain. Training a large language model means running that machinery for months, consuming as much electricity as a small town to adjust trillions of numbers by tiny amounts. Which raises the obvious question: why can no one else simply build the same chip? Others have. Google, Amazon, and a dozen startups have designed silicon that matches NVIDIA on paper, sometimes beating it. But the chip was never the moat. For nearly 20 years, every graduate student, every researcher, every engineer has learned to write code in CUDA. Millions of programmers, thousands of specialized libraries, Textbooks, university courses, conference papers, decades of accumulated tricks and fixes and habits. A rival can copy the transistors. It cannot copy 20 years of human muscle memory. Software written for a chip in 2010 still runs on the chip released this year, an unbroken chain of compatibility that no competitor can offer. Switching away means rewriting everything and starting again from zero. This is what economists call a moat, and it is the oldest one in technology. Not the machine, but the language everyone already speaks. There is a second moat, harder still. NVIDIA does not manufacture its own chips. Almost everyone is made in Taiwan by a single company, on machines built by a single Dutch firm. Those machines carve circuitry with light so precise it is generated by vaporizing droplets of molten tin 50,000 times a second. There are only a handful of such machines in existence, and NVIDIA has spent 30 years earning first place in the queue. So the supply chain narrows to a point, a global industry worth trillions, balanced on a few clean rooms on one island in the Pacific. In 2023, the world understood. When conversational AI arrived in public hands, every technology company on Earth discovered it needed the same thing at the same moment. Orders arrived faster than factories could fill them. Waiting lists stretched to a year. Chips were shipped under armed guard.